Good day, viewers all over the world. My name is Yemi Toshade. It's time to talk. Jonah Bush, science, technology, and mathematics. And I'm also an advocate of STEM promotion in Nigeria. And this afternoon, I want to talk about the topic that is very fundamental to STEM to all that we have in science and mathematics. And I refer to it three fundamental physical quantities. Three fundamental or basic, three basic physical just like food, shelter, clothing is fundamental, three basic fundamental human needs for survival. In science, over the years, currently and in the future, these three physical quantities are the foundation when you use anything about science. Without them, there is no science. They give meaning to all the technological products that we are enjoying today. Actually, there are actually 10 fundamental quantities in science generally. The first three are the three most important ones. These are the ones we want to discuss. Then the next four, then the last three. So the first seven are the basic one, while the last three are the supplementary. Today is not the day for me to dabble into that. At the appropriate time, we'll talk about that. But these three fundamental or three basic physical quantities are so fundamental to our scientific daily life. There is no individual on earth, except a dead person, that will not engage in these three physical things on daily basis. What are these three physical quantities in STEM? Number one, we have mass. Number two, we have length. Number three, we have time. Every living human being engage in these three basic quantities on daily basis. Mass. If you want to drink water, if you want to add salt to whatever thing you are cooking, if you want to take a bit of toothpaste to brush your teeth, you have to measure it. That is mass. Length. Even within our domestic activities, we move from one place to the other, move from one room to another, move from one edge of the kitchen to another. That is length. How much more traveling from one state to another, from one country to another, but whatever means of transportation, that is length. Time. We are guided by time on daily basis. The time we need to go to bed to take a snap and rest, the time we need to sleep in the night, the time we need to wake up, the time we need to go up, to church, the time we need to go to the mosque, the time we need to do one thing or the other. So just like food, shelter, clothing is needful for our human existence, these three quantities are the foundation. Whatever equation you might have ever come across in your life, either in the past, currently, or in the future, must be subject dimensionally to these three physical quantities. So the mass, the symbol is capital letter M, length, capital letter L, then time, capital letter T. So they are so important that for any equation to exist, they must conform to this. And there is a unit of measure of these three physical quantities that are basic in our daily lives, in our scientific world. For mass, it is kilogram, capital K, small g. For length, meter, small letter m. Mind you, it's different from this capital letter M, which is a symbol or dimension for mass. Dimension for length, capital letter L. Dimension for time, capital letter T. The unit in abbreviated form for mass is kilogram. The unit in abbreviated form is meter, small letter m. And the unit for time is small letter x. In science, capital letter X means distance. You come across that under equation of motion. You are not there for today. Now, today, I want to quickly take us through the application of these three basic physical quantities in the just concluded West African Examination Council exam physics. The part 1 of that particular exam paper, the question 1, has to do with one of the application of these three major physical quantities. Like I said earlier on, any equation must conform to a balance in line with these three physical quantities, their dimension in particular. So there's what we call dimensional analysis. We go to that right now. Dimensional analysis, and how we use that to check or to derive equation in the STEM world. So we have dimensional analysis. Dimensional analysis. So like I said, I will be making reference to the first question in part 1 of the just concluded WAEC paper part 1, the first question. I will read it, then I will put on board the vital things that I needed to write as we solve the problem. The force F acting on the wings of an aircraft moving through air of velocity v. So there is an F, there is a v velocity, and density. This is the symbol for density, rho, density, is given by the equation. So we are given an equation. Look at the equation. We said F equals to K, there's a K there, there's a V raised to power X, density raised to power Y, and area raised to power Z. Where K is a dimensionless constant. That means this is a constant. For it to be dimensionless, that means it does not conform to any of the physical quantities, basic or none. Now, an area A is the surface area of the wings of the aircraft. Use dimensional analysis to determine the values of X, Y, and Z. We need to find what X, Y, and what Z stand for. Now, this is one of the application of basic quantity, or if you like, basic dimension or symbol in science. In this case, we'll be making reference to ML3 and MLT, the first three most important ones: mass, length, and time. Now, for F to be equal to this, it means that dimensionally there must be a balance. After the analysis, it means that whatever dimension that is at the left hand side must be exactly what is obtainable at the at the right hand side. That's what there is equals to, mean balance. And so dimensional analysis helps us to know if an equation is correct or not correct. That's number 1. 2, it helps us to formulate an equation. Like in this case now, we want to know the equation that is connecting these variables: F, the force, velocity, density, and area. And all that I just told is that they are connected. But how they are connected, we do not know. So we will know by analyzing this dimensionally. Now, fundamental things you need to know are this. Number one, what is force? Force is mass times acceleration. Mass times acceleration. And mass is capital letter M, is fundamental. Acceleration is velocity over time. Dimensionally, acceleration is L meter per second squared, which is L per t squared. That is force for you. You need that one. Another one is velocity. V. That's number 2 thing you need to know. Velocity. Velocity is displacement over time. Displacement means length. The only difference between displacement and length or distance is that displacement is a vector quantity, distance or length is a scalar quantity. So that is why speed and velocity they share the same unit, meter per second. So velocity is displacement over time. That means length per time. Length per time. Another one we need to know, which is number 3, which is very important to our analysis, is density, rho. Density is mass over volume. Mass over volume. Anything of capacity, anything volumetry has 3 lengths combined together. We'll come back to that another time. So mass is M, capital letter M, that's the symbol. Volume, that is per L raised to minus 3. Because the unit of volume is meter cube or centimeter cube. So it means the dimension is L raised to 3. Then area now, thank you. Number 4, area. Area, let's take the simplest form, area of a rectangle. Length times breadth. Length is L, breadth is also L. That is L raised to 2. So you need to understand this first. That's the first thing you need to understand. And we're going to be making reference to this. So now with this, we'll come back to this. The force is this. Our force is M LT minus 2 equals to, this is dimensionless. It means it has no unit. So you just leave it there or you take it as 1. You can take it as 1. Just take that K. Yes, number 5. You can assume that K to be equal to what? 1 is of no effect because it is dimensionless. It means it does not conform to any of these mass L and T. Okay, so we have that. Then our velocity is already L per T. L per T. That is L T minus. Then raised to power what? X. Density is M per L raised to minus 3. That's M per L cube. M per L cube. That is this. M L minus 3 raised to power y. Then our area is L squared. The dimension of area is L squared. So we put it there. L squared. Then raised to power z. Now, the analysis requires some splitting and some knowledge of indices. You have to apply law of what? Indices. We know that if you have A raised to power n, everything raised to power n, this n multiply this. So it will give you A raised to power n, n. Again, if you have B raised to power k, D raised to power n raised to power 2, these exponents multiply all these exponents individually, provided what joins this B and D is product, is times. It's only when what joins them together is addition or subtraction that will not be applicable. Okay, so we quickly apply that here. So here we have M now, MLT minus 2 equals to, now let's apply that concept I just explained just now here. This one is L, that is L raised to power 1. Because one exponent, what is there is actually what? 1. So 1 times this, that will be L raised to power x dot 1 minus 1 times x, that will be t raised to power minus x dot. We are opening up all the bracket now. This is m, no exponent. It is 1. You assume that it is 1. 1 times y, that is m raised to power what? Y. Then minus 3 times y, that is l raised to power what? Minus 3 what? Y dot. Then here what we have 2 times z, that will be n raised to power 2 what? Z. Now, the left hand side of this equation is equal to the right hand side. And see, there is no addition, plus sign or negative sign, subtraction sign joining those variables, those dimensions. Then we can rightly compare with the indices or index. We can compare index in an attempt for us to get the problem solved. So I will come back to that here. We compare index. Let's see it. Alright, done. Get that done. So we compare. Let's start with comparing m. Comparing m, both sides of the equation. Here, the power, the exponent of m at both sides. Here, if you look at m here, this one is 1. This is also 1. So we have 1 equals to, anywhere we have m here, only this case, right? Okay? What is the exponent? Y. So we know that is equation 1. Equation 2, we compare the dimension n, capital letter N. At the left hand side, we have only the exponent as 1, that is 1 equals to, at this side, we have n raised to power x, the exponent there is x. We have it here again, another one, that is plus minus 3y, the exponent is minus 3y. Then we have here again plus 2z for this. So we have 1 equals to x minus 3y plus 2z. That is equation 2. Then compare the last one now, which is our, let me clean this so that we can get it done properly. We compare the dimension t. For the left hand side, the exponent there is minus 2. It must be equal to, let's look at this side, we have it here, t raised to minus x. So that is only where we have the dimension t appearing there, that will be minus x. And the minus cancel minus, you can see it, so that means 2 equals to what? X. That's equation 3. Now, this is a very simple one because we already know 2 out of the 3 variables, the 3 exponents. We already know our x should be equals to what? 2. Our y to be equals to what? 1. So we need to find our z. So if you look at equation 2 that we have generated, we can get our z. So from equation 2, we have 1 equals to x, our x here is 2, minus 3 bracket, our y is 1, we put 1 there, plus 2z, we don't know z, that's what we are looking for. So this is 1 equals to 2, minus 3 times 1, that's minus 3, right? Plus 2 what? Z. So we have 1 equals to what? What is 2 minus 3? That's minus 1 equals to what? 2 what? Z. Collect like terms. Oh, sorry. Plus 2z again. You are looking for z. Take this to the other side. That will be 1 plus 1 equals to 2z. So what do we have now? We have 1 plus 1, 2 equals to 2z. I'm looking for z. I will divide both sides by 2. If you do that, our z will give you what? 1. So we now know our z to be what? 1. Our x is 2. Our y is 1. Our z is what? 1. So that equation can be written like this. That equation cannot be written as f, which is k. What is it? Okay, v raised to power x density raised to power y, and area raised to power what? Z. So let's substitute that. That will be F equals to K. This one is 2, that will be V squared, right? Y is 1, that will be this. Z is also 1, that will be this. So this is the formula the examiner is trying to bring across to us in that question paper. So that is one of the application of dimensional analysis, and it comes from the 3 basic what? Physical quantities in what? In STEM. Just like I said at the beginning of this class, I said that just like food, shelter, and clothing are important for human existence on daily what? Basis. The same thing goes to mass, length, and what? Times. We engage in those physical quantities one way or the other on daily what? On daily basis. And much more importantly, they are the foundation to whatever discovery, experimental investigation, empirical test that we want to achieve, that will lead to the formulation of equation or formula. It has to be subjected to those physical content. That's why they are fundamental. That's why they are basic. Thank you. See you in my next class.